So in this video, we're going to learn about covalent bonding. So what is a covalent bond? If you have your flashcards, you can use those, or you can just think about the answer in your head. Is a covalent bond A bond that one atom donates an electron to another atom? Is it B, a bond where an atom donates 2 electrons to another atom? Is it a bond where the nuclei of 2 atoms fuse? Or D, is it a bond where 2 atoms share at least 1 pair of electrons? Take a minute to guess. Hopefully you remembered from grade 10, it is sharing. Covalent bonds are all about sharing electrons. So it's a bond where 2 atoms share at least 1 pair of electrons. So in a covalent bond, what you're going to get is an unpaired electron from one atom. We'll find an unpaired electron from another atom. And what they'll do is instead of one atom giving electrons away to another, like you would in an ionic bond, they actually share each of their unpaired electrons, so both win. And now both atoms have a pair, which is exactly what they want in order to have a complete valence shell. When we have that situation, so you have shared pairs of electrons, that's a covalent bond, and we call the thing that you make, the compound that you make when it's held together with covalent bonds, we call it a molecular compound. It has another name too. I'm going to write it in. It's called a molecular compound or a molecule. So when you hear people talking about molecules, what they mean is somebody that's held together by shared pairs of electrons, by covalent bonds. That means you have a molecule. If you had something held together by ionic bonds, you'd have an ionic compound. But covalent bonds is a molecule or molecular compound. All right, so what does this look like? Let's look at fluorine bonded to fluorine. So here I've got 2 fluorine atoms. Both of these have 7 valence electrons, right? You can see this 1, 2, 3, 4, 5, 6, 7. That's because fluorine is a halogen. It's in group 17, so it's got 7 valence electrons. So fluorine is not happy. It does not have a full valence shell. It needs 1 more electron to be full. But it's not like a bond with, say, fluorine and sodium, where sodium wants to give away 1 electron. You've got fluorine and another fluorine. Neither fluorine wants to give up an electron. So what do they do instead? Well, this unpaired electron right here and this unpaired electron right here, they're going to go visit each other and they're going to share. So I'll just erase that. So these guys are going to come closer to each other and they will share. So what we get is a shared electron pair. Now if you count up, how many valence electrons does fluorine have? 1, 2, 3, 4, 5, 6, 7, 8. This purple fluorine, including its shared electron, has 8 valence electrons. So 8 valence. My apologies for my bad writing. I don't have a pencil. So 8 valence electrons. That means it's got a stable full octet. It's got a stable valence shell. The red one, same deal. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So that fluorine is happy. So that's what the Lewis dot structure looks like. And we circle those shared pairs just to make it obvious that you know which ones are shared. When we draw this as a line diagram, I'm going to replace that shared pair with a single line. So notice that a shared pair, that's 2 electrons, becomes 1 line because that shared pair of electrons is the covalent bond. And so we draw it as a single line when we draw it in an organic chemistry line diagram style. So there's a fluorine bonded to a fluorine for us. So each line diagram, just replace your shared pair with a single line. Let's do a trickier one. Let's say we have to do carbon dioxide. So carbon dioxide is a molecule, it's a molecular compound, all held together with covalent bonds. Carbon is in group 14, and so it has 4 valence electrons. I've drawn them there. Oxygen is in group 16, so it has 6 valence electrons. And there are 2 oxygens, O2 here. Now I've put their valence electrons intentionally in weird spots because of how I'm going to bring these together when I bond them. You can play around with carbon dioxide a little bit and try moving the electrons to different spots, but what you'll find is the only way to give everybody 8 valence electrons, which is what you need for a stable octet, is to actually share 2 pairs between each oxygen and the central carbon. So what you'll see is I have a shared pair here, a shared pair here, a shared pair here, and a shared pair there. When I do that, I have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around this oxygen. So I've got 8 valence, which is stable. And I have 8 valence electrons around the carbon. 1, 2, 3, 4, 5, 6, 7, 8. And 8 around oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Everybody has 8 valence electrons. Everybody's stable. So carbon dioxide is happy. So these are all shared pairs, right? That's all shared electron pairs. So we can draw each shared pair as a line. So we're going to turn this shared pair here into one line, this shared pair into one line, this one into one line, this one into one line, and it looks like this. So what we see is carbon double bonded to oxygen. So when we have two shared pairs, we call that a double covalent bond. You can guess one shared pair is single, 2 is double, 3 is triple. So again, in that line diagram, we're replacing an electron pair with a single line. Let's try water, very important one. So water is made of oxygen, which has 1, 2, 3, 4, 5, 6 valence electrons, and then 2 hydrogens. Each hydrogen has 1 valence electron. So what's going to happen here is that this valence electron from one hydrogen will come and join this unpaired electron from the oxygen, and this valence electron here will join this unpaired electron. So we'll kind of do this. That'll make a shared pair, and that'll make a shared pair there. Now oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, so it's happy. Wait, hydrogen doesn't have 8. That's okay. Hydrogen has 2. And hydrogen has only 1 energy level, right? It's in period 1, so it only needs 2 electrons to have a stable valence shell. So everybody's stable, so everybody's happy here. So this is what water looks like. So each of those shared pairs, they're called the bonding pairs. These ones over here are called lone pairs, and they actually are important too. They influence the shape of these structures. And as we're going to get into a little bit later, the shape really matters for polarity, which is how negative and positive different parts of your molecule are. Water is a polar molecule, and it wouldn't be without those lone pairs, so they're pretty important. Let's draw that as a line diagram. So to make it a line diagram, I'm going to replace each of these shared pairs with a bond. So that's one bond, and this is one bond here. And I've oriented it differently, but it's the same idea. We've got 2 lone pairs, 1, 2 lone pairs, 2 covalent bonds between this oxygen to that hydrogen and this oxygen to that hydrogen there. And that's water, a fundamental molecule of life, super important one. So now I'd like you to pause for a minute and try and draw the covalent bonding of ammonia. So ammonia is 1 nitrogen, 3 hydrogens. Try and draw it on your own. All right, you can unpause me now. Hopefully you've all tried to draw it. Let's give it a shot. Hopefully you got that nitrogen has 5 valence electrons because it's in group 15. Hydrogen has just 1. So what will happen here is you'll get the 5 valence electrons from nitrogen, 1, 2, 3, 4, 5. Each one will welcome a single electron from hydrogen. This one's from a hydrogen, this one's from a hydrogen, this one's from a hydrogen there. And what we get is nitrogen with an octet that's stable. It's got 8 valence electrons, and hydrogen has a stable valence shell with 2 for each of the hydrogens. If you turn that into a line diagram, what you'll see is you have a lone pair of electrons and then covalent bonds, single covalent bonds from the nitrogen to each of the 3 hydrogens. And that's how you make ammonia, which is NH3. All right, next try drawing ethane. This one's harder. You've got to have 2 carbons and 6 hydrogens, and somehow they have to all fit together to make something that works out. Notice that carbon has 4 valence electrons because it's in group 14, and hydrogen has just 1. See if you can make that work out so that everybody has a full octet, a full valence shell. Give it a go. Hopefully you had some success. I'll tell you how it works now. So here's some drawings of it. So the carbons are each going to bring 4 valence electrons. So here's one from carbon, here's one from carbon, here's one from carbon, and here's one from carbon. Now I'll show you the other carbons. This carbon will bring this one, this one, this one, and this one. So 4 from each carbon. And then each hydrogen will bring its own valence electron. So 1 here, 1 here, 1 here, 1 here, 1 with this hydrogen, and 1 with that one. So what you end up with is just a bunch of single bonds everywhere. And so we can draw it in the line diagram like this. Single bond between the carbons and single bond between the carbons and 3 hydrogens on each carbon like that. So that's ethane, which is C2H6. Everything, single bonds everywhere. Here is ethene. I'll show you this one. This one's even trickier. So ethene has C2H4. In order to make this all work, and I've already kind of color-coded it for you here, you'll have one carbon brings 4 red electrons there. The other carbon brings 4 red electrons. In order to make these carbons happy with enough electrons around them, because they need a stable octet of 8, right? They're going to actually have to have a double bond in the middle. So they need one shared pair there and another shared pair there. And then each hydrogen will come in with 1 electron. Now if we count up how many electrons does each carbon have, it's 1, 2, 3, 4, 5, 6, 7, 8. So he has 8. And this one, 1, 2, 3, 4, 5, 6, 7, 8. It has 8 as well. All the hydrogens have 2, so they're all stable as well. This is what this looks like as a line diagram. We can turn each of these shared pairs into a line. So we'll notice there's a double bond here between the 2 carbons. So that's called a double bond. You still have single bonds with the hydrogens, right? But it's a double bond between the carbons, and we call that ethene. You'll learn in grade 12 a little bit more about how you name those, like ethane versus ethene. That actually comes down to those double and single bonds. Let's try nitrogen next. So let's say you have N2, nitrogen bonded to nitrogen. Nitrogen has 5 valence electrons. Take a minute, pause this video, and try and draw this yourself. All right, hopefully you figured out that what you need here is a triple bond. That's the only way to make those nitrogens happy. You actually need 3 shared pairs. So nitrogen bonded to nitrogen looks like this. You'll have 2 lone pairs, each one on each side of the nitrogens, and then 3 bonds, 3 covalent bonds in between your nitrogens. So that is your triple bond right there. The last thing we need to know is diatomic covalent bonds. Diatomic compounds are really important. We are going to use this all course. So maybe put like a big star beside this part of your notes so that you remember to memorize these. Diatomic just means when you have an atom that bonds to itself. So hydrogen can bond to itself. Here's what happens. Each hydrogen comes with 1 valence electron. They share, and so each hydrogen now has 2, which is a full stable shell for hydrogen. And it looks like this, just hydrogen single bonded to hydrogen. But there are others, and these are the ones we need to memorize. There is hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So these 7 atoms, anytime they're just hanging out by themselves, if they see another of themselves around, they're always going to just naturally become a diatomic molecule. They just want to be in that state. So when we're doing reactions, if we ever make oxygen, it's never going to just be O. It'll always be O2. So that's why we need to memorize these so we're ready for our reactions unit and we know which ones will form diatomic compounds. There is a way to remember them that is a little bit easier, which is to use your periodic table. So what you have is if you like hockey, this is the puck over here. There's the hydrogen. And then there's the hockey stick. It starts at nitrogen, goes over to fluorine, and goes down to iodine. You might want to put a line around this on your own periodic table on your page so that you can remember how to find those diatomic molecules. So hydrogen forms H2 And then everybody on this hockey stick forms forms a diatomic thing as well. So N2, O2, F2, Cl2, Br2, and I2. So it looks like a little hockey stick with a puck. Hopefully that helps you remember how to do that.